And we're live. All right. So we're going to be talking about shared memory multiprocessors today, mostly how do you implement shared memory multiprocessors, coherence, consistency, and all that good stuff. So yeah, before we get into this, anything anybody want to address? Questions about, I don't know, project assignments?
Yeah, I had one question.
Yeah.
I think I saw originally the A2 due date was like the 23rd, but another post I saw you're just making it the same as the final day of class. Which one's correct? Is it the final day?
Yeah, it's the final day. Sorry, but which I've not updated the website, I guess.
Maybe, I mean, I haven't looked at the website. I know that was the date, and then I saw the updated Piazza post. You may have updated the website. I haven't
Okay,
checked.
I'll check to. I'll try to make it consistent. It is everything like anything that's due is due on May 4th.
Okay, sounds good. Thank you.
Because that's the last day that anything could be due.
Cool.
Yeah. Cool. Other clarifications, questions, comments, anything? All right. I guess if there's nothing else, yeah, I can always put things up on Piazza. Let's get into this. So, we've talked about how you would build a single processor till now, right? And then last, I guess, 2 classes we were looking at how do you build a multi-core, multi-threaded processor, an SMP, CMP, and then multi-threaded as well. So when you kind of get into this realm of having multiple processing units that are accessing memory, you have this decision to make of, do you want to have each, do you want to have that memory, all of the memory in the system be accessible by all of the processors, or do you want to have it, different? Now, typically we've gone in the direction of shared memory multiprocessors. So, all the processors in a particular machine have access to all of the memory, even if, some of them have faster access. There's still, like, in some cases, one node may be trying to access memory from the other node, and that may be slower than, if it were to access its own memory, but you still have access to the other side as well. So that, we're going to call these shared memory multiprocessors. The way this kind of works is you build this abstraction of an address space, and then the address space is spread across all of the main memory in the system. We're kind of seeing this actually kind of break down with other compute devices like GPUs and things that have their own memories and then they're not shared. But let's not go there yet. So when you have, something like that looks kind of like this, you have 4 processors, they're connected to a memory system, then there are many times when you need to communicate between processors, right? So communication can be implicit or explicit. What I mean by that is, let's say processor 1 and 2 were, accessing the same data. And so if both of them read the same data from memory, not an issue. Sharing is fine as long as neither of them changes the data. Now, if one of them were to change the data, right? So say P1 does a write, you need to update the copy that P2 has so that they see the same data. Now, you could do it in one of 2 ways. You could have P1 explicitly send a message to P2 saying, hey, I changed the data, here's what it is. Or you could have an implicit communication where P1 just writes that new value back to memory, and then it's up to, like, a update kind of propagates to P2, but not explicitly from P1. So we've kind of typically gone into a implicit communication model via loads and stores. An explicit communication model would have been message passing. Message passing is another thing you will hear in software design as well, right? Like where um, processes send each other updates and messages, things like that. So there's a theoretical foundation for this way of doing things. It's called the parallel random access memory model. We're not going to be looking at it, but if you're interested, there's a reasonably good Wikipedia page that you can look it up. That's the parallel RAM model is more useful for people designing kind of algorithms to take advantage of multiple processes sharing the same memory. But it's sometimes can be useful to look at it as well. So why shared memory, right? Why not go with separate memories or something? The benefits of going with the shared memory model is that the application, when you're writing an application, you see a single. You can kind of think of your processor as one big processor that is able to run multiple tasks at the same time. So you can think of it as a multitasking uniprocessor, even though it's actually multiple cores. And so the OS and system software above kind of needs only to evolve every so often. And you can kind of communicate with loads and stores without involving system software in this whole thing. Now, if you had to do an explicit or a split memory thing, and you had a shared OS, then you would actually need system software to kick in to move data between the different memory domains, and that would of course add overhead. Maybe you could speed that up, and there's a bunch of research on that as well, but let's not go there right now. What's the downsides of going with shared memory? Well, synchronization is hard, is complex. So you got to implement that in hardware. It's complex. We'll look at what that specifically means. Communication is implicit, so that becomes hard to optimize because you don't have semantic information. You have no idea of what it's going to do. And shared memory models don't scale very well. We'll see what we mean by that as well. But SMPs and CMPs are the most successful models that we've seen for computers so far, and they're pretty successful even as general machines, right? Like they're multi-billion-dollar markets. But just because something does financially well doesn't mean it's optimal, but it's evolutionary. Like we keep changing. We keep changing system designs as workloads evolve, as constraints evolve. So what does that mean, right? Like, what is shared? Like, how would you implement shared memory in a multi-core processor? So you can think of it being two ways. One, you can have a separate CPU and memory. So every CPU is connected to the bus, and every piece of memory is connected to the bus. And they kind of all have, all-to-all access, equal latencies. So any core can access any memory at the same latency. Now this is, good in one way because it has that equal uniform memory access characteristics, but it has lower peak performance because the distance you have to travel, and then you have to kind of synchronize with everybody else who may be using this bus or whatever. So your peak performance is lower. On the other hand, you can have memories be tightly coupled with processors, right, with CPUs. So this is non-uniform memory access, or NUMA. It has a faster local memory, and then you can access other cores' memories, but they're higher like they're higher latency access, right? So in this style, placing your data close to the CPU that's going to use it is more important. And the benefit you get from doing that kind of a placement is you get high peak performance, because now the access, you don't have to contend on the bus to access that piece of memory. It's like yours. unless somebody else is, also trying to come in and access. But then their latency is much higher, right? Because they have to go over the bus and maybe talk to your controller and so on. So even if we took the second case, we're actually seeing a lot of machines go this route because it scales better. You don't have this contended bus in between, even if you were to implement it with a mesh or a torus or whatever we saw earlier. It actually makes a lot more sense to go this route because then the nodes can kind of be tiled and get scale. How would you implement the connections, the interconnections? So again, there you have many different choices. We're just looking at two here. One could be a shared network, for example, a bus. Now buses tend to have low latency or uniform latency access to all other um, uh, pieces of memory, right? So you can go from CPU 1 on this side to CPU 4's memory here, and it would be the same latency as going to CPU 2's memory, because you just have to master this bus, go there, pick it up, and come back. However, this tends to also be a low bandwidth model of interconnection, and this doesn't scale beyond like a certain number of cores, typically around the order of 16. Once you get to 16, the contention on that bus is so high that you're not making useful progress. Cache coherence here is really simple, right? If we haven't quite explained what coherence is, but coherence kind of is if two CPUs are accessing the same piece of data, the same memory location, how do you know that they're seeing the writes or the updates the other one's seeing? How are they seeing this, having a coherent view of that piece of data? That's kind of what we're looking at. And so that is very simple to implement here because you do a broadcast. You just say, hey, I changed, OX dead beef. It was 1, now it's 2. That kind of gets broadcast to everybody. If somebody has that line in their cache or whatever, or in their memory, they make that change, and that's easy. Now you could also implement it with like a point-to-point network instead of a shared network. This would kind of be like an example here is this thing where it's a kind of a mesh. This CPU is connected to this one and this one, but if it wants to reach this memory, it has to go either these 2 hops or these 2 hops, right? But some memories are further away and higher latency to access than others, but this kind of a network scales really well to like thousands of cores. So you can kind of assume this is a tile and just kind of print tiles in a 3D, in a 2-dimensional array or 2-dimensional matrix. That's because you can have good bandwidth between these things. But then memory placement becomes an issue, thread placement becomes an issue, because you want to keep things that are communicating with each other very close to each other. And then implementing cache coherence is a nightmare because you're now thinking of you're kind of approximating a network of like internet, interconnected machines. And you can think of each CPU as its own computer, and like the thing that you have in a network, like on a LAN or on a LAN. So then you kind of have all these delayed broadcast changes and things like that. So coherence becomes a bit of an issue. Yeah, just this stuff makes sense till now. I mean, we're talking about this stuff at a very high level, right? So we're not going into too much actual details for any of these things. Any questions so far? Okay. So if we were looking at like point-to-point networks, which are becoming quite popular. You could also organize point-to-point networks, this way, which we looked at earlier, or more in a more hierarchical fashion, right? Like this kind of works as well. And at some point, the trade-off between these two, for example, is cost, right? It's area on the chip and the cost to manufacture any of these things versus performance. So if you were to build, something this way, you kind of have more like if traffic between these two is, you know, traffic that does not cross this boundary can stay within this router, and so um, the load on this router can be a lot less. So you can have, maybe different performance characteristics between this link and these links. Right, there's a lot of variety of things you can do there, um, and that's assuming that that particular example, for example, assuming that you have less traffic moving between the two different nodes, um, and so on. So these router chips, are essentially, you think of them as like routers that you see in internet, or the wired network stuff. So these are called indirect, these are directly connected chips. The distinction here is really not that important. So yeah, we're these are some, just a brief overview of like some different ways of connecting processors together, and this is its own like whole area of research. Network on chip. How do you design these networks? How do you lay out cores next to each other? And these things are getting more and more interesting with questions of like, you can have CPUs that don't look like each other, that operate very differently, that may have different assumptions about consistency or coherence, etc. How do you interconnect those? How do you interconnect a CPU and a neural network processor? Right? How do you build those kind of things? And there's a whole range of questions that people are working on and implementing in this space. But for all of these kind of, however you choose to implement the shared memory system, there's two big things that you need to solve, that, there are different solutions to this, of course, but these are the main important ones. And you'll see kind of, these are concepts that you'll see, in a distributed system setting, you'll see in processors, and, between machines, etc. The two big things really are coherence and consistency, right? They're closely related, but they're not the same, and they're often confused. So before we get into it, does somebody want to make an attempt to kind of define coherence and define consistency? Maybe with an example. And I can start the example off, right? So it's tax season. You got to file taxes. What would coherence look like for I don't know, filing taxes? The operation of filing taxes, not saying software. Whatever. Like if that was considered an operation, what would coherence look like? Does that make sense? Or you could use another example if you prefer. Somebody? Anybody want to try? I mean, you don't have to be. It doesn't have to be right. It doesn't have to be perfect. what is coherence. I think some of you may have encountered this in other courses in operating systems or. No? Okay. Um, so yeah, just keeping with the example I was I just started off with, coherence would be um, answering the question like, okay, let me broaden the example. Let's say you wanted to file you want to file taxes, and let's say you got to mail in your tax forms. So there are three things that you need to do. You need to fill out the form. You need to and then you need to kind of have an envelope and glue and stuff. So you need some stationery, and you know having both of those is a prerequisite to kind of putting the form in the envelope, sealing it, and mailing it, right? So you could parallelize. Let's say you don't have the stationery, you can kind of parallelize both of those tasks, where you can have one person fill out the form and one person go to the store, buy stationery, and come back. Now, coherence would be um, the shared state of, you know, have you filled out the form? Have you brought the stationery, right? In order for you to finish the final step, which is to kind of put the forms in the envelope, seal it, and mail it, you need to have a coherent view of whether both of these tasks were finished. Um, the you can't be that, or actually maybe a better example is yeah. So let's say the third person, let's say the third person was mailing it. So two people were, one's finished filling the form, one's buying stationery, and the third person's mailing it. Then there's two pieces of data that need to be coherent to the third person who's mailing it. One is, did the first person finish filling the form? Did the second person buy the stationery? And then have you received both of those, right? So that's coherence. Coherence is on the operation or the piece of data, right? Did you fill the form? Did you buy the stationery? Did I receive both of them? That's kind of what coherence is. Consistency is ordering among these operations. It doesn't matter uh, whether like if both of them are running in parallel, one's filling the form, one's buying stationery. It doesn't matter if they kind of occur like this, where you fill the form first and then the uh, person gets the the envelope, but kind of both need to, those, there's a dependency there where both of those need to happen before you can mail it, right? Otherwise, funny things happen. Like you're mailing an empty envelope, you don't have an envelope, but you just kind of put a stamp on the form and mail it, or something funny like that. So that's consistency. Consistency is um, seeing a consistent ordering of events in a system, seeing an ordering, a determinable ordering of events in the system. Now that's consistency. Did that make sense? People have questions on those two? We'll, of course, get into this as well. No questions? Okay. Just making sure you guys can hear me, right? I'm not talking to myself.
Yes.
Okay. All right. So, more uh, concretely, I guess, in terms of processors, coherence, uh, let's say variable A initially has the value 0. Now P1 stores 1 into A, and let's say P2 loads A from memory, and now sees a value of 0, right? Um, but these operations have, uh, you know, let's say P2 loads A from memory after P1 has written 1 to A, but then that value has not been propagated back to main memory, right? It's sitting in P1's cache. So P2 sees an out of date or a non-updated um, value for A. This could lead to errors in the system where, as you wrote your program, you assumed that, you write that one and it should be visible to P2, but P2 is seeing the wrong thing. So you need to do something to keep these P2's cache coherent with P1's cache. Right. So that's another example of the same thing is, if both of them had already loaded the old value, you make one change from one to the other, but nothing happens. There's no change because you're not seeing the update is not getting propagated to the other cache, right? Um, so um, how would you get around this? What solutions can you come up with that would help keep these caches coherent? What do people think? What ideas do you have as to um, how you could um, keep the caches coherent? What's the most basic thing you can do? What's the most obvious thing you can do? Or is it non-obvious at all? I don't know.
Would it be to have some type of bus between P1 and P2?
I mean, there is a bus between P1 and P2, right? I, I guess I didn't understand you.
Well, I thought that bus would be handling the coherency between the caches.
Yes, I mean, you're going to implement that, but I guess how would you do that, right? Like that's the question that we're really answering. No, so what's the most like performance be damned? How would you get correctness between P1 and P2 given how they're organized, um, no matter what else happens?
So when one cache writes to a line, it has to order some type of like invalidate command for that line to every other cache.
You Another way, you could kind of do that is to write that back, right? So you make one change, you have to propagate that value out to main memory. And then since you're putting that value out on the bus, you can also kind of say, hey, if anybody has this value, change it now. How would that perform? Or how would that kind of look? How would you build that? Like there were two cases that we saw here. One was that you loaded the value after the write happened, and then the other one was that both of them had loaded the old value. So let's handle the first case first, right? Like where the second processor loads the value after the write happens. So the kind of the thing we came up with was to flush uh, the value as soon as you write it. So would that solve the first case? Is the question clear? Are you guys getting what we're talking about, or is this just all really vague and confusing? Or is it just that like the question I'm asking you don't have an answer to, but you understand everything till now?
I think it's clear. I'm not sure exactly how we would fix it. Like what exactly you're asking for. If it's like a hardware piece that we're adding or how to implement the bus.
Okay, fine. So but the question till now, I mean, sorry, the things we've seen till now are fine, right?
For the most part, yeah. At least for
Okay.
me. You can speak.
Someone else wanna like does anyone have issue understanding? Would anyone like me to repeat what we've gone through till now?
The bus is in two direction, right? It can like move up from the main memory to the cache, and it can be from the cache to the main memory, right? It's
Yes,
not one nothing.
yes, the bus is can be, yeah, it's multi-directional. Yes.
Yes.
Okay. Okay, so fine. Let's kind of let's dig into this, and we'll come back to. Oh, I just kept moving forward. Well, we'll figure out the answers to what we were just talking about. So, the problem here is that one processor writes to its own cache, and you need to have some way of letting other processors that may have the same line know, or may later acquire that line, for them to know um, that the value has changed in somebody's cache, but has not been written back to main memory. So one like the software-based solution is to flush every time you make a flush or an invalidate instruction every time you do a write. Now this is going to be very expensive because flushes have to wait for a response from memory before you can continue with the next memory operation. And so it's a write, right? Like writes need to be updated. So then you're kind of blocking the load store queue, right? For a lot of traffic that may not even be necessary, but this is a correctness guarantee. Like you can install these software-based solutions by a compiler or runtime system, but it's hard to get correct because sometimes you may have memory aliasing, where you have two virtual addresses referring to the same physical address, but you have no way of knowing that they're referring to the same physical address, right? So that becomes a little difficult. Software-based solutions do exist. They're for things like there's some types of processors that build software-controlled caches. So you can have a cache that does not have a controller of its own, and they implement the logic for when to bring something in, when to evict it, is left to the processor. So this stuff does exist, but far more typically you'll see these written into hardware, just because it makes it easier, right? You provide some guarantee of coherence, and software above just becomes easier. So the way you'd kind of build coherence, if you had a write-through cache. So write-through cache is one that writes back for every time it um, every time you do a write, you don't just update the cache, you also write it back onto the bus, right? So there's this allows multiple readers, so you can have the value on multiple things, but then all caches kind of must monitor all bus traffic to make their copies of all data coherent, right? So if I were to do a store, the you would write the one, but then you'd also kind of broadcast. You'd say bus write a equals 1, that gets written back to main memory, and because that operation also happened, you have to invalidate A in processor 2's cache, and it has moved from a valid state. So the thing in the bracket here is the validity of that cache line. You've just invalidated that A, right? So there's a very simple state machine to implement where it just says if any processor does a write, kick that line out from every other processor, right? But it also means that now P2 has to go and fetch the new value every time, and sometimes that may lead to bad performance. It also means that you need to snoop on all bus traffic all of the time, right? So this is implicit things. So like I said, it's very simple protocol. It can be represented by like this state machine. So the actions that a processor can take are load, store, bus read, and bus write. The bus messages are bus read and bus write, and you track 1 bit per cache frame, which is valid or invalid. Now, if you stay invalid, if you're in the valid thing, if you do a load, you're still valid. There's no transition. There's no operation. If you do a store, you got to do a bus write, but you can stay invalid. Now, if you see a bus write on, if you're a cache that's been holding the valid thing, you did nothing other than observe a bus write, you have to transition to invalid. And then if you were to later do a load, if you were to do a load, you can go back to valid, but then you also have to kind of broadcast this bus read, right? So because you need to check if anybody else is, you need to inform people that you're reading that. Actually, the read happens from the bus, so that's kind of why you're doing this bus read. If you're in the invalid state, you just stay in the invalid state. If you were to do a store in the invalid state, you would kind of remain in the invalid state, and your operation is invalid. So that's for write-through caches, right? Stuff that writes both to the cache and then back into lower level cache or memory or whatever. For write-back caches are you just write to the memory, and the write-back happens later at some other time, which typically is caches that we like to implement because they don't require as much bus bandwidth in the steady state, right? Like you don't need to broadcast an update every time that you change something because maybe that data is not shared. You only need to broadcast when that data is shared. So that kind of means you need to start a new piece of information, which is ownership. Who has this data, right? If you're the only owner, right? Like when the owner has the only replica of a cache block, you can update it freely, no problem. There's no issue with that. If you are multiple readers, so nobody really owns the state, you're just all like sharing it or you're borrowing it, then that's totally okay too. No bus traffic required. You just do independent loads. This needs to be a state transition in the current state, but we'll see that later. The only restriction here is you cannot write to that value in your cache without gaining ownership. Now, ownership is a property that only one person can have. There can only be one owner of the state. Otherwise, you end up in an undefined state. You can't determine whose operation was the right operation, right? Like whose operation occurred first, who had the power to do this. There's some arbitrary ness in gaining ownership. If two things try to gain ownership at the same time, one of them is going to win, the other is going to lose, and that's, there's no guarantees on that. When you do a new read, you must check if there is an owner, and if there is an owner, you take that ownership away, right? You need to transition to a state where there is no owner. That's because assuming that they're all doing reads. So this coherence protocol is the simplest one, at least, is called MSI, Modified Shared Invalid. The processor actions tend to be load, store, and evict, right? Bus messages are bus read, bus read exclusive, bus invalidate, bus write back, and reply. Some of these messages can be combined, but we're going to look at them independently. And then there are three states to track per cache frame: invalid, shared. Shared means that the cache has a read-only copy. It has to be clean. That means cannot be modified. The data cannot be dirty, right? You cannot have written something to it. And it has to be up to date. That is, you have the latest version of the data. And then there's the modified state, which is the cache has the only valid copy, it is writable, and it is dirty. So you'll only transition into the modified state when you do the first write, and then you can stay there as long as you keep writing and nobody else wants to read, right? And if somebody else wants to read, you then have to write that back out and transition to the shared state. So a simple example of the MSI protocol, we start out with P1, P2 both having the address A as invalid in their caches. A is in memory with the address 0. There's a bus connecting the two processors. So you start out in invalid. Let's say you do a load, which then requires a bus read, and you transition to shared, right? So now you issue that bus read for A. You get the value back. A in P1's cache is now in the state shared, and it has a certain value. Now, once you have the value shared, you can load that value as many times as you want, and you still remain in shared. There's no broadcast required for that. So you can have another operation. You can have another processor do a bus read, and at that point you'll get this bus reply from processor 1 saying I'm also shared. I'm also sharing this data, and here's the value as it exists, right? So this reply kind of exists because the data at that point may have been modified, and actually I'm not sure about that one. Maybe not. Let's keep it as let's get into the reply later. So yeah, right. And if you were to do an eviction, if you were to evict A from processor 2, you transition processor 2's cache state back to invalid, right? And so that's the thing you're seeing here. The state is tracked per processor or per cache line per cache. So A remains in the shared state in processor 1's cache, and that cache line transitions to invalid because of an evict in processor 2's cache. So they're separately handling that. And so now that remains invalid. So let's say processor 2 decided to store A, right? It had read the value earlier, or it's doing a blind store, whatever that may be. So let's say you do a store, you kind of first, need to read the value for A, but you also kind of need to declare that you want exclusive access to A. So that's why we call it the bus read X. X here stands for exclusive. So when you do this store, you issue a bus read X, you get the value, and then you kind of move to this modified state. And from the processor one's perspective, it wasn't shared state. It saw the bus read X, and it actually has to send a bus reply and move to the invalid state. So we'll see this. So you did the store, you issue the bus read X, both processor one's cache and memory. Look at this. That transition happens. It says, yes, I've invalidated my copy. I'm done. If there were other processors, they would all have to invalidate their copies, send back a reply. And then you transition in P2's cache from, in this case, invalid to modified, and you're allowed to do your change, right? Thereafter, any operations that processor 2 does, because it has the only copy, it's guaranteed that has the only copy of A in all caches, can stay in the modified state, load, store, whatever. It doesn't have to do any broadcasts. It just has, all rights to that piece of data at the moment. So let's say that's the state of the system. Processor 1 now wants to load the value of A. It wants to operate on A, right? So processor 1 will say load A. The cache will issue this bus read. The bus read, for processor 1 is going from an invalid state to a shared state, right? So it wants to do this transition. But the processor 2 is now in a modified state. So when it sees a bus read, it must now give up its exclusive access. So it has transitioned from the modified state to a shared state. But it also has to essentially make sure that this value that it currently has is visible. So you'll see a bus reply with the value in that. Maybe actually what happens is it writes that back to memory. I mean, it actually just puts the value for A onto the bus. The memory controller picks that up and updates its own copy. At the same time, the cache, P1's cache also picks up that value. Now, both of them transition to the shared state, and they stay there as long as they're both reading from that cache line and do not make any modifications, right? So now let's say like where that shared state where if there's the where both of them have the data in shared state. Let's say one of them wants to do a write, so you do a store. So now you want to transition essentially from shared to modified, because the only case that you can do writes in is when you have one processor has exclusive access to that one cache line. That's the only way to kind of make sure that you don't end up with two things thinking they wrote to the same thing and then some random some random value shows up. So when that happens, when you're in the shared state and you want to go to an issue, you want to do a store, you send out an invalidation for A, you send out this bus invalidate signal. That bus invalidate signal, when it's received by a different processor, which was in the shared state, goes back to invalid. So it changes to invalid. And then it sends out the reply saying, yeah, I've invalidated my thing, right? The reply may not be needed, but we'll see. I mean, the reply may not be needed if you've not modified anything, right? Like if you haven't changed the data, you're in the shared state, you just invalidate your cache line and move on. There's no requirement for explicit reply. And so we end up in this state, right, where this one now has modified the cache line A, it is written 2 to it, everybody else has A as an invalid line in their cache. which means they don't have A in their cache. Now, let us do a store on processor 2, right? So somebody else has a modified state, you're invalid, you do a store, so you're here, you're invalid, the processor 1's here, so you do a exclusive read, the other processor has a modified value, it sees that bus read exclusive, it has to reply. So it does reply, it transitions to invalid, it broadcasts its value of A, which then goes to this processor, which has transitioned to modified, and it does its own value. But note on this particular case, we've actually not updated memory yet. The data is just ping-ponging between caches, cache lines. And only when you actually do an eviction, you evict the memory, the line from that cache, does it actually go back to main memory. So these are two separate operations. One is, you can have two processors kind of ping-ponging buffer lines between themselves. Classic way that I think people test this thing is they write two threads that read and write to the same, they both write to the same piece of memory, the one line, and that buffer just keeps bouncing between the two. So predictably that has some pathological performance, because you're just stressing out the coherence controllers on both of these caches. So it's a bad way to write code, but you can use it to test these things. So yeah, this is MSI. It's the actions that a cache can take are load, store, evict. And then the bus actions are read exclusive, invalidate, write back, and reply.
I actually have a question.
Yeah.
Could you go back to the previous slide for a second? So the only time that, well, I guess the question is, so does P1 and P2 always update their values from the bus? Like so you had memory is only updated when there's that write back call. So does that mean the other processes rely on whatever is in the bus, not what's in main memory, to get their right values?
So that only happens if the memory that cache line is actually loaded into anybody else's cache, right? So if you issued a load and you heard back nothing from any other cache, but you heard back from the memory, so the memory will reply, will send you a reply saying, hey, here's my version of the thing. But if another cache does reply as well saying, here's my version, the cache's version always takes precedence.
Great, thank you. Yeah, that's what I was wondering.
Yeah. Because you cannot write back to memory without also invalidating your own cache. So there's that guarantee as well. Like when you issue this, this write back, bus write back, you have to transition your state to invalid. You cannot be maintaining that memory.
What would go wrong if you maintain that memory?
So you could end up with, well, if you maintain that memory, it's not that you can't guarantee correctness there, because I guess you could have both the memory and the bus and the cache reply to any load requests, but then that it kind of violates the the simplicity of this model where you have one owner, either memory owns it or the cache owns it. So it's just part of this protocol is that you don't do that. I mean, it's not that you cannot have the two, like those two keeping the values as long as you keep, as long as you both of them reply to a request to a load. The only issue with that is, sometimes messages can get delayed, they can get lost, right? Because you have a shared bus. Maybe the bus is not able to respond. So then your loading cache may receive, if it receives two messages, the messages may, one may get lost and you may use the wrong value. So it just becomes a lot more complex. So a simple way of dealing with this is there can only be one value of the correct value of the system can only be in one place if it has been updated.
That makes sense. Thank you.
All right. So there's actually a whole bunch of other protocols that fix certain, not correctness issues, mostly performance issues that arise with MSI. So there's MESI, which introduces an exclusive state as along with a shared state. So there's modified exclusive shared invalid, and then there's MOESI, which I don't even remember what the O stands for. Anyway, I don't think we're kind of getting into those, or maybe we will. We'll see. So yeah, moving on. That's the simple way of keeping cache coherence. But when you're implementing cache coherence, there's a couple of things you need to consider. One is bus bandwidth, right? If you have a bus, for example, then everybody contends on that bus. Only one person can broadcast at the same time, and so you have there's a scaling issue there, where after a certain number of participants on that one shared substrate, you end up just like not being able to get any work done. So it's more scalable option, which we saw last class, was like something like a mesh, where you can communicate one-to-one without kind of disrupting other one-to-one communications. So that's one alternative. And then because whenever you do a broadcast, whenever say you're doing a bus read or a write, your processor's caches, each cache has to kind of listen to every broadcast and then, if needed, do something. But a lot of the times when you listen to a broadcast, that you don't have anything to do. You're not involved in that transaction, right? And so the there's a lot of messages on the bus that are not necessary. They don't need to go to everybody, and they're still there. So, and then that you prevent just localized broadcasts. And two processors are like the snooping hardware is just sitting there listening to all this stuff that has nothing to do with it. So you can change something that you can change there is you can replace this non-scalable broadcast protocol, which is to spam everybody, with a scalable directory-based protocol, which is only spam those cores that care. A directory-based protocol is exactly what it sounds like, which is for every cache line, you have some lookup directory, and there's an entry in there for okay, for this cache line, here are the cores that are interested in these in participating in these transactions, and then you only kind of send the updates to those things. So you've kind of gone from a case where you're just putting it out on the bus and everybody listens to everything, to it gets propagated to only those who care. Now, directory-based coherence protocols are more complex. You need to extend memory with, or you need to add another piece of hardware somewhere, typically in memory, that tracks caching information, right? So for each physical cache line, a home directory tracks the owner. If a core that has a dirty copy, or the M state, and any shares the cores that have clean copies. Of course, you can't have anybody. You can only have one M state and then no shared states, or you can have many shared states and no M state. And then the cores, each core will send coherence events to the home directory. The home directory is, if you have multiple banks of memory, the directory associated with that bank that the data was drawn from. And so you send coherence events to that directory, and then that directory sends events to any cores that care, right? So kind of, just a simple approximation. Let's look at how this would kind of work. So some cache has a miss on a load instruction. Let's call that one L, and H is the home directory, right? So you'd send, when you have a miss on a load, L will send a read request to the H. H will read reply if it, has if the data is in memory, and that's the simple read transaction. Let's say the L has a miss on a load, but the block was previously in modified state in some other cache let's call it R, right? So you send the read request to H. H says, what is the state currently maintained? State is modified, owner is R. So then you send, the home directory will send a request called a recall to R, which says, I'm revoking your modified state or your ownership of this cache line, return the value to me. So you reply to that recall with the data, and then H will reply to L, and now is it being shown here, but the state has to transition to S, and the owners, then there are no owners, but there'll be sharers, which is L and R. You can also kind of speed that up by making this a 3-hop read transaction, which is you ask for the thing, you forward the read request to R, and then R replies with an ACK and sends the data to L. So you kind of cut off one hop here. There's some issues here, which is, you could end up in a small amount of race conditions with the MSI protocol. Let's say L has a dirty copy, wants to write back to the home directory into memory, and R concurrently wants to read that piece of memory, right? So you launch this write back request to H. At the same time you launch, R sends a read request to H, and H may say the state is modified and owner is L, and so it forwards that read request. But then L thinks that, hey, I've written that back and I don't have any data, right? It says, oh, write back and forward read, so no need to ACK. So it sends some value back, but then this was all kind of happening. The read request transactions were all happening before the write back request had reached H. And so finally, when the write back request kind of reaches H, you now have this issue where you're not quite sure what the final state of the system is. So to get around this kind of a race, you actually need the kind of messy state that I was talking about, which is just the introduction of complex intermediary states to ensure that you don't end up in a race like this, right? So let's say you were trying to do this basic read operation. You try to do read A, it's a miss, you go to the directory. A makes a note saying shared by, A is shared by, let's say, number 1, and it sends back the data for A, right? And let's say you're trying to do write on the right side processor, and then you send this read exclusive for line A to the directory. The directory then sends an invalidate to L. L has to drop that value from its cache, and then you transition from shared number 1 to modified number 2 in the directory. You send back that acknowledgement, and once you receive the acknowledgement, you can send the value of A to R, and the R is free to make any modifications it needs to. But an important thing here was the important difference to note here is in the non-directory based coherence protocol that we were looking at earlier, when somebody wanted to do a write, you would transition from shared to modified, and then that would cause everybody else to invalidate. Here, you actually need to transition from shared or whatever to an exclusive state, right? And make sure everybody else has invalidated their copies and are not doing any other operations on the same data before you can actually transition to the modified state. So that kind of becomes that modified exclusive shared invalid. And so I think, yeah, we're just, brief look at how coherence is implemented. There's more complex ones that you can look up if you're interested. And yeah, with that, we'll probably stop here, actually. Questions so far? Does anyone want me to repeat anything? Is something not clear? Stuff, I don't know, went over your head and you don't understand what's going on at all. I hope that's not the case, but do say so if that's the case.
I have a question.
Yeah.
The directory, is it like all the execution, like can they parallel or them like in order? I mean, like, because we have the direction go down, so.
Sorry, could you repeat that? You're dropping off your.
We have the L and the R, so they can send a request to the directory at the same time, right? Okay.
Sorry, and what? They can send a request to the directory and what?
At the same time, like.
Yes, they can send They can send a request to the directory at the same time, which is why you end up with that race condition that we saw earlier. And so to prevent bad to prevent an inconsistent state from, or incoherent state in this case, from occurring, we ensure that that's kind of why you introduce this exclusive state, where you have to transition into an exclusive state before you do a modification, just to prevent a misordering of two things resulting in a system becoming incoherent.
Okay, I got you. Thank you.
All right, other questions? We have about 5 minutes for, I don't know, anything people want to talk about. All right, I guess if no one has any other questions, we'll stop here. I'm going to stop the recording.